Can everyone hear me okay online? Is this okay? Perfect. Okay. So, yep. Hi, everyone. Yep. Thank you to everyone online who is attending as well. So today, Tathagata Saha is going to be talking first. So he's a PhD student at the Copernicus Institute in Poland. And he's going to be telling us a bit more about this idea that Johannes introduced about predicting the reliability of your fits based on simulations. So yeah, whenever you're ready, Tathagata, please take it away.
Okay. Hello, everybody. So I am Tathagata Saha from the Nicolaus Copernicus Astronomical Center of the Polish Academy of Sciences in Warsaw. And today I'm going to discuss BXA-driven study of reliability of X-ray spectral fits in determining AGN torus morphology. So this work has been done in collaboration with my supervisor, Professor Alex Markowitz, and with Dr. Johannes Buchner, the author of the package BXA. And it's based on our recent work published this year. So yeah, before I go into the main results, a brief introduction. So classically, non-blazar AGNs are classified into two types. That's type 1s and type 2s in optical, and unobscured and obscured in X-rays. So in optical, the type 1 shows broad emission lines of hydrogen, for example, the hydrogen Balmer lines, along with some narrow emission lines. And in type 2s, you see only narrow emission lines. In the X-rays, the intrinsic absorption of the X-ray continuum is the basis of classification. So the unobscured case has almost no absorption, and the obscured has an absorption corresponding to a column density of 10 to the 22 or higher. So these two subtypes are broadly correlated with each other. That's type 1s are generally unobscured in X-rays, and type 2s are generally obscured in X-rays. And this can be explained on the basis of the presence of obscurer, popularly known as the AGN torus. So in a type 2 situation or obscured situation, this torus actually blocks the intrinsic emission from the X-ray emitter and also from the broadline emitter, thus resulting in this type 2 or obscured phenomenon. And it's broadly depicted as shown here as a thick dusty donut. And this is actually the simplistic picture of an AGN torus. However, with recent studies, it has been seen that this torus is much more intricately connected with the accretion inflows and the outflows processes of an AGN central engine. So our theme today is the X-ray view of this torus. And yeah, on the left at the bottom, you see the spectrum of what is known as the cosmic X-ray background. And one of the most important features of this spectrum is the near 30 keV hump. So this broadly coincides with the Compton hump region of a broad class of AGNs, and that makes us think that and that AGNs are a major potential contributor to the cosmic X-ray background. And out of these AGNs, we think that significant fraction of these AGNs are obscured AGNs. On the right, you have the distribution of the line of sight across various redshift slices, and we see that the distribution is the distribution is kind of uneven in different regimes. That's the unobscured cases. The unobscured are shown here in red, and the obscured you see here. And on the extreme right, you have the very heavily obscured or Compton-thick X-ray obscured AGN. So these kind of studies are correlated, and the analysis that goes into these, for example, in the figure on the right, is mostly dependent on X-ray fitting. So concentrating on the only heavily obscured AGNs the models of the obscured AGNs that goes into the fitting, it kind of determines the results that we get. So yeah, so these results are generally model dependent, and a few suite of models that can go into the fitting of this kind of or analysis of this kind of data are shown here. So you have the MYTORUS model, which is basically a dusty donut from Murphy and Yakub 2009. And here you see the cross section of such a donut here. On the left, you have the CTORUS model, which it's basically a clumpy model, which where the clumps are distributed in a very thick biconically cut out shell. And you also have one otherwise continuous model, which is biconically cut out, called Boros. So all these models can be used for studies as shown here, as shown in the previous slide. So what the basic analysis, that the basic work that these spectral models and these models do is they take the emission from the central X-ray source, which is basically a power law, and then reprocesses it in the torus materials to generate the reprocessed emission. For example, you have the photoelectric absorption and the scattered and the other reprocessing via Compton scattering. So we're going to discuss that a little bit later. So all these models are basically simulated for Compton-thick, simulates the spectrum of a Compton-thick X-ray obscured AGN. And with respect to studies like the ones previously shown, we want to test that how reliably these models can determine the parameters of, for example, the line of sight absorption of the sources. So in our work, we basically ask two questions. So for nearby Compton-thick CFERs with typically high intrinsic flux, and given the best instruments both in the softer and the harder X-ray bands, and a typical exposure, are the parameters of the torus and the very central engine recovered? And can we distinguish the different morphologies? So to do that, we adopt a very simplistic spectral model of Compton-thick AGN and base our studies on simulations of this very simple spectral model. So here are the various spectral components. So you have the 0th order continuum, which is basically the photoelectric absorption, which is marked in red in this figure. So this red dashed curve is the photoelectric absorption. So you have the Compton scattered or reflected component, which is marked here in blue. So the blue dashed line here. And you also have a soft scattered component or a warm mirror, which can occur due to the reflection from hot electrons, which is present distantly. So these two components originate from the torus material and all this totally generates a spectrum like this. And with the base torus emission, we add some soft components, which are basically just to simulate some contamination in the softer band, which are modeled via EPIC. So the total expression for this spectral model thus becomes something like this. So you have this added components from the transmitted, the reflected, and the soft scattered component, and then you have also the softer contamination components, and all this is absorbed through a galactic absorption column. So that gives you the total spectrum. Now we use this total spectrum, which is marked here in black, this black solid curve, to simulate the data from the instruments like XMM-Newton, EPIC PN, and NuSTAR. So we assume a typical flux level around of 0.5 milligrab with typical exposure times of 100 kiloseconds on XMM and nearly 50 kiloseconds on NuSTAR for each module, and we use expect-fake to generate the data like this. So here we have an example of instrument convolved spectra, which is basically generated using this black curve here. So we then perform the analysis of this the spectrum of the simulated spectrum. So we use BXA multinest for this purpose. So we perform two different classes of analysis. One involves the intramodel fits, which is when the simulated data and the fitting model. So the data, the model under which the data is simulated and the model that goes into fitting are the same. And with that, we try to test the status of parameter recovery. And we have cross-model fits where these two models, the simulation model and the fitting model, are different. And with this, we check the model distinguishability and the parameter discrepancy if it exists. So in the multinest runs, we adopt flat priors for almost all parameters, which are either for all parameters which are either uniform or log uniform, and we assume a C-stat likelihood, and we are interested in posteriors and the evidence values. So also we assume two different classes of spectra. One is medium Compton-thick spectra, which involves column densities while simulating the data to be lower than 2 × 10⁻²⁴. And these spectrum are generally transmission component dominated, which is this blue curve here. And we also have spectrum from the heavy Compton-thick regime, which has very high column densities, and typically above this value. And these spectra are reflection dominated. So this value is not a very hard value. It's so it's just an approximate boundary that where the scattered component starts to dominate with the strong attenuation of the transmitted component with increasing column densities. So spectrum are generally simulated in these two regimes, so for varied column densities. And we'll find later that this will affect the nature of the posteriors that we get from BXA fitting. So yeah, the results from intramodel fits. So this is an example of fitting from the model called UXCLUMPY, which is a clumpy torus model. And so the distribution of the clumps in this model is based on a Gaussian. So more clouds are congregated near the equator compared to near the poles. And at the very center, you have an inner Compton-thick ring, which is optional, but we simulated data with it and also performed the fitting. And at the very center of this ring, you have the X-ray source. So here are the posterior distributions when we perform intramodel fitting. We use the same model for fitting. And in all these posteriors, this black dashed line the region between these black dashed lines marks the 90% confidence region. And the red is the input value that went into data simulation, and the green are the median values. So when the red lines or crosshairs remain within this dashed lines, we say that the parameters have been recovered. So we see that most of the parameters are recovered here, and with various degrees of accuracy. So the line of sight absorption has been recovered quite well, given the strong presence of the transmitted continuum in the medium Compton-thick regime. So is the intrinsic the photon index of the intrinsic power law. However, other parameters, for example, the sigma parameter or the cloud distribution parameter here, it's recovered with large errors. So this is nearly 30%. And similar case is seen for theta, which is the line of sight, the angle of inclination. That's this I here. Another example from CTORUS, another clumpy model. So we have we have line of sight absorption and the photon index recovered pretty well with low errors. However, the number of clouds, which in the radial direction, which is a parameter here, has been recovered with pretty wide posteriors. It's almost unconstrained. So what we learned from this intramodal fits is that various parameters are recovered with various degrees of accuracy, and some would be definitely recovered better, and some would be recovered much more with much more errors. So we also test the instrument dependence of these parameters. Again, for UXCLUMPY, the CLUMPY model introduced before, we performed three different runs of BXA, one for only XMM data, one for only NuSTAR, and one for the joint. So we find that the posteriors in the NuSTAR analysis, NuSTAR only analysis, is quite well constrained. However, for the XMM, we find that it's quite spread out, and it shows a little bit of bimodality here. So it's not very well determined. And the joint fits definitely has a much better posterior. So again, coming back to the NuSTAR energy, XMM and NuSTAR energy range. So XMM is generally towards the softer X-rays, and NuSTAR is mostly towards the harder X-rays. And the effect of this Compton-thick ring is generally seen in the harder bands. So it's basically covered by NuSTAR, and that's exhibited by the posteriors. So you need to determine your instrument when you try to measure something like this. Yeah. Now, dependent on the regime, so we have, this is for the line of sight absorption in the medium Compton-thick and heavy Compton-thick regime. So on the left, you have the single posteriors from both the regimes, for both fits from both regimes. So the x-axis is actually the values, and it's normalized with respect to the input. And we find that the medium Compton-thick regime, the line of sight absorption is much more localized. It's recovered with much less errors. However, for the heavy Compton-thick regime, it's much more spread out. And to check the statistical validity of this, we perform 100 different BXA fits to 100 different spectra, simulated all under the same conditions. And we get a distribution of their discrepancy. That's median minus the input values, as shown here. So again, the discrepancy is much higher for the heavy Compton-thick regime, and it's much more localized towards lower values for the medium Compton-thick regime. So this is mainly because of a heavily attenuated zeroth order continuum for high column densities. So you cannot measure the line of sight absorption in such high values of NH. So because it's dominated, the spectrum is mostly dominated by the scattered continuum. Also, for parameters of morphology, have in the medium Compton-thick and heavy Compton-thick regime, these are the results of 100 different BXA fits for 100 different spectra, and we plot the 90% confidence regions for each of these fits for each of the spectra. So in the heavy Compton-thick regime, it's the parameter, for example, the sigma parameter of UXCLUMPY is much more localized to lower values. So the 90% confidence region is much more localized towards small numbers in the prior range. And in the medium Compton-thick regime, it spreads over to much higher values. So similar thing is seen for the R by R, which is the donut thickness parameter of Rx torus, which is another donut model, and we see the same trends for this. So this implies that we have lower statistical errors for parameters of morphology, mostly in the heavy Compton-thick regime. This is mainly because the scattered spectra is much more dominant in the heavy Compton-thick regime, and the imprints of these morphological parameters are seen mostly in those mostly for those of these parameters are seen mostly in the scattered spectra. So yeah, now to the cross model fits, when we have a different fitting model compared to the initial simulation model. So this is data simulated under UXCLUMPY and then fitted with different other torus models that are listed here. So what we get are very discrepant posteriors for gamma, which is the intrinsic photon index. So we have, for an input value of almost of 1.9 for UXCLUMPY, we get these varied values for other models. So this can be attributed to the difference in the shape of the spectrum, which are generated by these models due to different effects. On the right, we have the line of sight absorption. So this is comparatively well determined, even though they're discrepant in some cases, with almost nearly 10% discrepancy. So again, when we move to the heavy Compton-thick regime, which are the results here at the bottom, so the line of sight absorption is much more discrepant compared to the previous case, and it moves to with an input for an input value of 5 times 10 to the 24. We get varied values of line of sight column densities. Again, mainly because the transmitted continuum is absent, and the gamma is, well, discrepant in some cases, even though it's not discrepant in some cases. It cannot be trusted for, it could be just an artifact of fitting. Another case we show here is the spectral fitting for an UXCLUMPY input using Rx torus. So here we kept the normalization of the transmitted continuum and the reflected continuum to be free for each case, and what we get here for an otherwise for a spectrum which otherwise does not have a transmitted continuum because it's simulated in the heavy Compton-thick regime, the fitted spectra using Rx torus shows a transmitted continuum just to adjust the shape of the Compton hump. So this results in a possible case for misinterpretation, and this is just an artifact of fitting, and determining physical parameters from situations like this, for example, the intrinsic luminosity of the corona, it can be misleading. So now we also test some cases for Bayesian model distinction. We assume we test how distinguishability varies with flux. So we assume we take 10 different spectra for 10 different levels of flux, where F is the highest level of flux, and we simulate these under a model CTORUS, and we fit it with these sort of models, so CTORUS, UXCLUMPY, and BORUS, and we define base factor to be the log evidence of log base factor equals log evidence of the fitting of a model divided by the evidence of that we get for the input model. So here is how the evidence, the base factor values varies with flux. So for XMM and NuSTAR, the joint fits, we get variation. We see that the base factor, the parameters are, the models are much more distinguishable for almost all levels of flux, because along this axis we have the base factor. It's much more towards the negative values here. However, for NuSTAR, the axis kind of expands. And we find that we move much more closer to our threshold values of -2, and the log base factor equals 0 values here. So this kind of suggests that band coverage is an important factor in determining for model distinguishability. And you have a broader band coverage, means the models are much more distinguishable. And for random fluctuations, which has appeared here near the threshold value, this can cause some troubles in terms of model distinguishability in lower flux values. We also performed 2 bulk simulations of 100 spectra for 2 different levels of flux, that's 0.5 milligrab and 0.05 milligrab for the model UXCLUMPY, and then fit it with UXCLUMPY and MYTORUS. And we then check the base factor distribution for all the spectra in these 2 different flux levels. And here the distribution is shown here. And in green, you have the results for high flux regime. So the base factor values are much more localized toward the negative values here, compared to the low flux regime, which is 0.05 milligrab, where some of the base factor values spills over to greater than 0. So we find that this number is 14%. So 14% of the selections here are wrong for the lower flux regime. And yeah, so the summary. So for all X-ray observers, we demonstrate how BXA can be used to understand the limitations of different model parameters. That's the degree of localization. The degree of localization that can happen in different model parameters given a data quality. And for X-ray torus model specifically, we show the limitations regarding certain model parameters under XMM and NuSTAR. So these can vary under different instruments. We also check how wrong model assumptions can result in discrepancy for different model parameters here. And this kind of shows the limitations of single epoch spectral analysis in determining the structural parameters of circumnuclear gas. So even for fluxes, which are quite high for nearby Compton-thick AGNs. So yeah, that's all. Thank you.
Thank you very much for a very nice talk. So yes, I just want to open up questions first to everyone in the room, if there are any questions at all.
Yeah, I was just wondering, your simulations in terms of number of counts in the spectrum. I guess that they have a lot of counts, right? It's even in your case of lower fluxes, it's
yeah. In case no, actually for our lower fluxes, it's count rates are pretty low.
Mm-hmm. Okay.
Yes.
Okay, thank you.
Any other questions? So I was actually wondering, so we've heard a lot about binning and what to do with the background. I might have missed it, but could you go over if you included a background in your simulations? And
yes.
Any sort of binning
with the background. Sorry?
If you used any binning or anything.
I cannot hear you clearly.
Can you hear me now?
Yes.
Yep. Sorry. So I was just curious if you used any binning in your simulations and fitting.
Yeah. So it's it's a minimum of 30 counts per bin for uniformly across all cases.
Okay. And
background, yes.
Okay. And do you think that any of the degeneracies that you see, or any of the results for, say, the intra-cluster fits, no, the cross fits, could be affected by the binning regime that you use, in particular in the low count regime?
We actually don't test how the correlations might affect. Like, for example, we for these cases, we are mostly interested in the base factor values. We did not check how it might affect for the constraints. And it's kind of understandable that the constraints would be pretty wide, like for example, in the high counts regime for morphological parameters, you get quite high errors or uncertainties. So this will be much worse in these cases, in the low counts regimes.
Right.
So,
okay.
Yeah.
So sorry, I didn't get when Peter asked about the binning. So did you do a particular binning?
Yeah, it's 30 counts per bin.
30 count per bin. Okay. Okay. So you use chi-squared?
No, this is C-stat.
Ah, okay. You still use
all C-stat.
Okay. See, I was just curious. Like in the lower flux, I would just be very interested because yeah, this is just very interesting with the scatter and the base factor. It's very cool for trying to find out how much information you can get out of the lower fluxes. It's very cool.
Yeah, I would say that like a proper background modeling can help in this case, probably in terms of determining the parameters if you are interested in.
Right. Okay. Mm-hmm.
Yeah.
Okay. Cool. Thank you. Okay. So, are there any other questions in the room? No. I think there was one question from Martin Topinka in. Oh, and one more on Slack. So, if we start with Martin's question. So, Martin asked, there are lots of posteriors that looked quite Gaussian. And so he's curious if using a standard maximum likelihood fit, say an XPEC, if you would get a similar result for when your posteriors are Gaussian like this.
I tried a few cases with simple chi-square fit, like you just load up the model and fit it with the same. You kind of retain the parameter values. You can get the values, but I haven't checked how the distribution looks like. So I would say that it will. Well, it's difficult to say without doing that. But yeah, but mostly for the cases which are well determined, for example, NH and this gamma, I think you can expect it to be symmetric.
Right. Okay, thank you. And then Aki on Slack has asked, was host galaxy obscuration accounted for somehow?
Yes. No, host galaxy means, okay, no, host galaxy has not been accounted because mostly these are heavy Compton-thick objects. So one additional parameter here, I don't think it's going to affect that much.
Yes, okay.
Although it depends on how much column density it has. But still, if you, for example, our galactic absorption column that we assumed is 0.1.
Mm-hmm. Okay.
So it's kind of high.
Yeah, that's quite high. Yeah. Okay, thank you very much. If there are no other questions in the room or virtually, then yeah, thank you, Tathagata, again.
Thank you.
Okay, and I think we might have